The role of computational complexity in modern science. Computational complexity is often regarded even by computer scientists, including the majority who are not theoretical computer scientists and whose concerns are typically quite practical, as a mathematically forbidding, isolated, and even largely irrelevant subdiscipline. It is our view, however, that the subject of computational complexity has a profound and even central role in modern science. The reason for this is that theories of computational complexity frame and focus the efforts of algorithm designers in certain directions, e.g., the quest for polynomial time algorithms, and often discourage the investment of effort both on problems that are identified as inherently intractable and ones that are formally regarded as asymptotically well solved and therefore uninteresting. What efforts are put toward the inherently intractable for the most part could be classified as trying to establish that they are provably hard. Since efficient algorithms are vastly more important than good hardware in the grand scheme of things, the effects of this framing percolate through all of science via the tools that are eventually supplied to the other disciplines by computer science. It is worthwhile keeping in mind that intractability must be coped with and problems must be solved in practical applications. Furthermore, it is important to keep in sight the fact that in applications, we are only dealing with a finite fragment of the asymptotic universe, so asymptotic classes such as P only approximate practical feasibility in the same way that classes like MP and P space approximate practical intractability. From an engineering point of view, there are certainly approaches to complexity other than the classical view which can yield significant insight and applications for practical problems. The point of view of the authors is that, as expressed by the motto of the former Nature's Gas and Garage on Shattuck Avenue in Berkeley, California, the role of computational complexity is to serve the community. The framework of computational complexity focuses efforts on particular goals and encourages the development of a corresponding toolkit of algorithmic ideas. These are used not only in the pursuit of the declared objectives, but also in the design of heuristic and approximation algorithms for problems that are hard, but for which, nevertheless, something must be done. The central concept in the modern study of computational complexity is the notion of asymptotic polynomial time complexity. As a model in the sense of empirical science of computational feasibility, this idea must be regarded as one of the most successful scientific models of all time. What this book is all about is a practical generalization of this basic idea, but one that requires a fundamental reworking of the foundations. A computational problem is said to be solvable in polynomial time if there is an algorithm that, given any input x of size n, where size is normally measured as the length of a reasonably succinct description of the input, produces the output required by the problem specification in time big O of n to the alpha, that is, in time bounded by c times n to the alpha for some constants alpha and c. Whenever n is large enough, n is greater than or equals to n0, despite the enormous latitude for misbehavior that this definition allows, e.g., is n big O of n to the 100 algorithm really practical? Such misbehavior almost never occurs. One common type of exception to this general rule is the kind of big O of n to the k, try all k subsets algorithm, described above for the data cleaning problem. The numerical basis for the success of the notion of polynomial time complexity as a model of computational feasibility is evident in the phenomena of combinatorial explosion that haunts problems for which no good algorithm is known. Table 1.21 illustrates the tremendous qualitative difference between polynomial and exponential running times. As a concrete example of the problem of a combinatorial explosion, suppose that our computational task is to put a deck of cards in order the problem of sorting, and that the only algorithm we know consists of repeatedly shuffling the deck, and after each shuffle, checking to see whether the cards are in order. If there are only 3 or 4 cards in the deck, this algorithm will work okay. Now imagine that we run this algorithm on a vast parallel computer architecture consisting of supercomputer processors, each doing a billion shuffles per second, with one such processor for every elementary particle in the universe, and the whole ensemble of powerful hardware running for the lifetime of the universe. Now, how many cards could we expect to be able to deal with using this algorithm? The answer is about 52. Polynomial time complexity has been a successful, well-behaved model of feasible computability because when one asks about the complexity of a natural computational problem, there are 2 outcomes that cover most cases. 1. The problem can be solved in time big O of n to the third. The folklore of algorithm design would indicate that probably with a bit more effort this can be improved to big O of n log n. 2. The problem appears to be hopelessly intractable. It is NP-complete, or worse, and the only known algorithms are about as efficient as the get-lucky procedure for sorting. In other words, when we can do anything clever at all, we can usually achieve polynomial time complexities with small exponent polynomials. This can be regarded as a fascinating empirical fact about the natural world of computational complexity. Most theoretical computer scientists favor some form of the conjecture that problems of the kind 2 are indeed inherently difficult and simply do not admit efficient algorithms until this is far from proved. The last 20 years have seen remarkably little progress toward a proof of the P not equals to NP conjecture, which is one formalization of this intuition and widely regarded as the most important unsolved problem of computer science and the foundations of mathematics.